Okay, so this is about the first couple of units in baby chemistry. We're going to go back and we're going to review it, add a little bit of extra information, and then ready to test. So, electromagnetic radiation, going back, you should remember that wavelength is the distance between two consecutive peaks or troughs in a wave. So if we have a wave, then here to here is a wavelength, or from here to here is your wavelength. And wavelength is lambda, the crazy upside down y, or whatever. It's usually measured in meters, but you will see it in nanometers too. So meters or nanometers. And what is a nanometer? 1 meter, or 1 times 10 to the 1 times 10 to the 9th nanometers is 1 meter. We have frequency, which is the Greek letter nu. This is the number of cycles per second that passes in a given point. So this is going to be 1 per second, or you may see it as hertz, or you may see it as seconds to the -1. It'll be written all 3 ways. And then speed, c, which is the speed of light, which is 2.9979 times 10 to the 8th meters per second. I don't know if our reference chart says 3.00 times 10 to the 8th meters per second. Or it would be 3.00 times 10 to the 17th nanometers per second. So we have all of our equations sitting here. We have for the speed of light, then we have E equals hv, or E equals hc over lambda, where h is Planck's constant. So that is 6.63 times 10 to the -34 joules second. So if you're looking here at our wavelengths, what can we say about the top one? What can we say about the wavelength, the energy, the frequency? How are the wavelengths? Long, short, what? Long wavelengths. What can we say about the frequency, low or high? Low. And what can we say about the energy? Low or high? Low. Okay, so these two are directly related, while these two are inversely related. So when one goes up, the other goes down. So if you know that relationship, then you should be able to answer these concept questions. So what about the bottom one? What can we say about the frequency? Is it high or low frequency? This one over here. High frequency. What can we say about the energy? High or low energy? High energy. And what can we say about the wavelength? Low or short wavelengths. Questions on those? The two, frequency and energy, are directly related. And then wavelength would be the inverse of those. So wavelength and energy are inverse, and wavelength and frequency are inverse.
So then isn't our first example wrong?
It says long wavelength.
Oh, sorry, I thought it said.
Let me go back and I'll erase that so we can see that better. Long wavelength. Yes. I don't know, can you?
I didn't say can, I said
Oh. You may when I'm done lecturing. All right. So next, let's do some calculations. Calculate the frequency of light that has a wavelength of 6.7 times 10 to the negative fifth centimeters. So frequency is what we're looking for, and we know that lambda is 6.7 times 10 to the negative fifth centimeters. So the first thing we need to do is we need to convert our centimeters to meters. So how many meters would that be?
-7.
6.7 times 10 to the negative 7 meters. So that's our lambda. And so we have several equations we can use, but the one that has frequency and lambda in it is our speed of light equation. So C is equal to lambda times nu. We know that C is 3.0 times 10 to the 8th meters per second. Lambda is 6.7 times 10 to the negative 7th meters. And frequency is what we're looking for. So solve for frequency. Get it to me in 2 sig figs. 4.5 times 10 to the 14th, and our unit is hertz. Or you could say 1 over second, or however you want to do it. Question on that? All right, calculate the energy of a photon of orange light with a frequency of 5.0 times 10 to the 14th. So we want to calculate energy when we know frequency. So which equation do we need? So we're looking for E, and we have nu. So E is equal to Planck's constant times nu. Planck's constant is 6.63 times 10 to the negative 4th joule second. Nu is 5.0 times 10 to the 14th to the negative, second to the negative 1. Seconds cross out. And what do we get for energy? 2 sig figs. You guys should be getting calculators out and be punching this in. Thank you. 3.3. 11th? I got negative 19. Is it negative 19? Negative 19 joules.
negative 30.
So I said you guys need to be punching this in the calculator. Questions? Let's go do a few more. Calculate the energy of a mole of photons. A mole of photons of orange light with a frequency of 5.0 times 10 to the 14th seconds. So we just figured out that the energy in the last problem, we found out the energy was 3.3 times 10 to the negative 19th joules, and that is for one photon. It wants to know what is for a mole of photons. So how do I go from moles to single photons to moles? Avogadro's number, yes. So for every 1 mole, there are 6.02 times 10 to the 23 photons. So to 2 sig figs, (2.0 times 10 to the 5th joules per mole of photons. So you've got to watch the wording because it might just ask for a single or a mole. So you'll have to convert that.
So would you recommend using the value that we got in the calculator or just the rounded value that we had for the last answer?
Well, if it was a running question, then I would take the one from the last, whatever you answered number 2 with, to take that into 3. So we use 3.3 times 10 to the negative 19th. That's the answer we got in 2. So I would bring that as what I'm using for answer 3. What's it change it to? It doesn't change it much, does it?
It changes it by 1,000 or 900.
But if we're talking about times 10 to the 5th, then it shouldn't be very much. If you take it to significant figures and scientific notation. All right, calculate the energy of a photon of light. So that's E. We're looking for E. With a wavelength of 425 nanometers. So that is lambda. So which equation can we use that has E and lambda in it? So E equals HC over lambda. So E is equal to Planck's constant, 6.63 times 10 to the negative 34 joules seconds, times speed of light, 3.0 times 10 to the 8th, or we need nanometers, so let's do 17 nanometers per second. And that is all over 425 nanometers. So seconds go away, nanometers go away, and we're left with joules. So I need 3 sig figs.
times 10 to the negative 19.
4.68 times 10 to the 19th, and our unit is joules. sorry. Somebody's umbrella. All right, let's do our last calculation of these. So the energy required to break the oxygen-oxygen bond is 496 kilojoules per mole. Calculate the minimum wavelength of light that can break the oxygen-oxygen bond in 1 molecule. So my first step is to take our 496 kilojoules per mole, and we need to convert that to joules. Once I've converted it to joules, I'm in joules per mole, so I need to get to molecules per mole. Or I'm in joules per mole, I need to get joules per molecule. So, for every 1 mole, there is 6.02 times 10 to the 23rd molecules. So that should get me joules per molecule. So our energy is 8.24. Is that what you guys get? Times 10 to the negative 19 joules per molecule. So now that we actually have it per molecule, we want to know what the wavelength of light is that's going to break that oxygen-oxygen bond. So we know how much energy it takes, so we need to know the wavelength. So we need to use E equals hc lambda, with E being 8.24 times 10 to the negative 19 joules per 1 molecule. And H is 6.63 times 10 to the negative 34 joules second times 3 times 10 to the 8th meters per second. It doesn't matter. You just have to, yeah, it really doesn't matter. If it doesn't tell you if it doesn't say what is the minimum wavelength in meters, then you just pick whichever one. And that is all over lambda, and we find that the wavelength is 3 sig figs. .41 times 10 to the negative 7th meters. So that's the wavelength that we need to break that oxygen-oxygen bond. So on the next slide is where we can look and see what is that. So somebody look at there and tell me on that next slide what type of light do we need? Ultraviolet. So ultraviolet is what is needed to break that bond. So we're going to look here real quick at our spectrum. You see that we have our different wavelengths, and this is in meters. We have our gamma, It's 10 to the 12th, and then we have ultraviolet, 10 to the 8th. You have your visible light spectrum, and then infrared all the way out to your radio waves. And then you have your yes.
So, is microwave waves the same as you use a microwave? It's like those?
Yes.
Okay, so do they have a microwave section before they made microwaves, or they just named microwave?
I think they had the microwaves, and then they made the microwave after that. I mean, because if it would have been using radio waves, I guess we would have called it a radio wave. Yes. No.
Say no.
We could.
Okay. So if you will look, you have our light spectrum, and we have, as you go, on the other side of violet is ultraviolet. On the other side of red is infrared. So we know that violet is going to be less than 400 nanometers, while infrared is going to be greater than 700 nanometers.
So why is it like when we look infrared lights and ultraviolet lights, we still see colors? Ultraviolet, you still see like, you still see red for the infrared. Like, how do you see that?
Mm-hmm. Okay, so let's take a look at this down below. Is you see the emission spectra and absorption, or emission of energy and the absorption of energy. So what happens when we have emission of energy? What happens with a photon? If you emit a photon, then what do? We will see it's emitted, in the form of light. So we'll get a little bit of light. And if you will please look and see the how it says energy, and energy, this should be increasing energy. And we have our energy levels, N1, N2, N3, and N4. So on this one is falling from N4 down to N1. So it's emitting that energy, going to its ground level. Whereas in the absorption of energy, we absorb a photon, and it will kick that electron from its ground state up to its excited state. Now, ground state is not necessarily N1. Ground state could be N3 and going up to N4. It's just going up to a level higher than what it is. So ground level is anything lower than what it falls down to. So you should be able to label these and tell me that here we're losing energy, our energy goes down, and here we are gaining energy. Now, over to the side, that color is a hydrogen adsorption spectrum. So what they did is they studied hydrogen, because hydrogen only has one electron, and so they could see what that electron was doing. And if you will see, the top one is the absorption of the spectrum. So when the electron of hydrogen gains energy, you get that absence of light in those little areas, those four little lines. And then when it falls back down to ground state and gets rid of that energy, you can see it kicks those electrons out, or electron out, and that's the emission that we will see. Kind of like a fingerprint, every element has its own spectrum, emission spectrum. Yes.
Do you know how that, have you heard about that paint that absorbs like 99.96% of the
Okay, so next we have like 3 more slides. So the Bohr model. So Bohr model studied hydrogen, and what we got from the Bohr model was that we have our nucleus, and outside it we have our electrons in these orbits. But it's not that, we have those orbitals. So what he said is when we gain and lose electrons or photons, so going from here to here, we would be gaining energy, whereas if we're going from here to here, we are losing energy, falling back down to the ground state. So the lowest possible energy state is 1 and 1, but that doesn't have to be the ground state. Your ground state could be 2, depending on where you fell back to. But the lowest one we can go to is 1. Questions? So why is this important? So this is only postulates for circular orbits of the electron, but what we know is the electron is more tightly bound. So as we get in closer to the nucleus, energy is being released from the system. This only works for hydrogen because electrons are moving all around the nucleus in circular orbits or orbitals. So this brings me to the Rydberg equation. Rydberg equation is only good for the hydrogen atom. If I ask you anything else, you cannot use the Rydberg equation. So for a single electron to transition from one energy level to another, we can use the Rydberg equation to figure out how much energy was lost or gained. So delta E is equal to negative 2.178 times 10 to the 18th joules. And you're going to multiply that by the 1 over n squared final minus 1 over n squared initial. So where did it start? Where did it end? From the nucleus. So which end did it start or gain from? So if we're looking here, we go from N1 to N2. Here would be from N4 to N1. Just depending on that. And we're going to do a couple of these problems. But remember, it is only for hydrogen. So star that, do whatever, so you do not forget. Huh? Yeah, the first number is just a constant. Squared, yes. So, what color of light is emitted when an excited electron in the hydrogen atom falls from N? So it wants to know color of light. And we're going from N5 to N2. So if we take, it says it's a hydrogen atom, so we can use Rydberg. So delta E is equal to negative 2.178 times 10 to the negative 18 joules. 1 over, so our final is 2, so that's going to be 2 squared minus 1 over our initial, which is 5 squared. So when we go from 5 to 2, what happens to our energy? Are we gaining or losing? We're losing energy, so our answer better be negative. So put that in the equation and tell me or plug that in and tell me what you get. So negative 4.57? Negative 4.57 times 10 to the negative 19 joules. But we didn't answer the question. The question says it wants to know what color of light. So we need to take our joules and figure out what the wavelength is. So now we're going to use E equals HC over lambda. And we're going to multiply, so 6.63 times 10 to the negative 34 times 3 times 10 to the 8th. And put that all over lambda. And what do you get for lambda? Okay, yes. So negative 4.35. Now, wavelengths cannot be negative, so we need to take the absolute value of that. So 4.35 times 10 to the negative 7th meters. So if we go back and we look at our spectrum, where is that at? What color of light is that? UV?
No, visible. Yeah, I can't read mine.
I think it's UV.
I can't read it.
Isn't visible from 4 times 10 to the negative 7 to 7 times 10 to the negative 7? So
4.
4.3.
It's just, I think it's right on the other side of ultraviolet. So the thing is anytime you land at N2, you're going to emit UV light. All right, anytime a electron falls at N2, you get UV light. If it falls to N1, you get visible light. Which transition results in the longest wavelength? So going from 5 to 2 or going from 3 to 2, who has the longest wavelength? Who's going to emit the most energy? If you're falling from the 5th floor to the 2nd floor, or if you're falling from the 3rd floor to the 2nd floor, which one's going to have more energy?
The first one.
The first one. So if you have high energy here, then what can we say about your wavelength? If it's an inverse relationship, then your wavelength is going to be shortest. So your longest wavelength is going to come from 3 to 2. Questions? So, like I said, if you're going out tomorrow night or something, then you need to start your homework tonight.